So welcome to the Northumberland CAS Community event. This evening we've got Laurence here from Insight Resources. He's going to talk about data logging with the Microbit. I mean, I don't know, some of you know me. I'm originally a physics teacher, and I'm a computer scientist as well. And I was passionate for many years, about data logging, and it's an area I think it's been forgotten about really. I talked to some schools that have got the data harvest kit, which is very expensive, but they actually don't know how to use it, and it isn't being used in some schools. But certainly the Microbit's definitely well established, and what Laurence has is some software to allow us to do data logging. So I'll just leave it to you then, Laurence.
So, I've worked with data logging for many years, and quite a lot of what I can show you is an accumulation of what I've done with children in school and with student teachers in my work at the university, Leicester University. If one wants to describe the technology of data logging, it's all about detecting and measuring a physical environment. Crucially, it's about collecting data in a regular way over a period of time. Its value to education in the classroom, in my opinion, comes about not by just the process of collecting it, but interpreting it and using the data that you collect to find answers to questions. And of course, it's a teacher's skill to plant ideas of questions in the minds of children. Let's get started with some examples of data logging. I'm going to consider this is an answer to the question: where's the best place to sit in a classroom? How even is the light? Do you want to be someone who hides away in a dark corner, or do you like to have lots of light on your work? Well, in this instance, the pupil carried a light sensor across a room. How long did it take? According to this, 20 seconds. And I'm using the iLOG software now. The iLOG software existed before the Microbit came along, and in recent years, I've adapted it for use with the Microbit. So we can see that if we were a lighting engineer, we wouldn't be very happy with this rather lumpy distribution of light in the room. Here's another example. Suppose I prepare my sandwiches and the day before and put them in a freezer. How long have I got? How soon shall I get them out in order to eat them at lunchtime? Now, what I did here was to put a probe right in the middle of a bread roll, and a second probe, temperature probe, in the crust on the outside. And I've got a third one, which is simply in the fridge. And so here we've got the three temperature readings logged over a period of several hours, about 6 hours, something like that. This brown trace is the temperature of the fridge. Well, of course, the temperature of the fridge is already minus 20 something. So this curve here represents the time it takes for the temperature sensor to adapt itself to its environment. This is the temperature of the crust, and this is the temperature of the inside, with a rather interesting flat bit there. But to get back to my question, how long do I have to take it out before I want to use it? It appears that it needs how much time. I'm going to get this tool out, which will help me measure time intervals. So this is when I take it out of the fridge, and it's 2.8 hours. So that's another example of data logging. This one here shows it's an example of a graph telling a story. I've been boiling a kettle, and I might ask the children, you know, what do these lines mean? What was I measuring? Well, it says up here that I measured sound level and temperature, right? Which one is which? And we've got a nice steady increase for one and a very bumpy ride for the other. Well, clearly this is the sound recording, isn't it? And a nice steady increase in temperature. So there's a graph telling a story. Right, let's come back to my PowerPoint. I'm going to skip the next one. With the microbit, this is really good news because the microbit comes with sensors built into the device. Here we have it, and on the reverse side, we can see some labeling there which indicates where the sensors are. The sensors that are available, there's an accelerometer. We can measure tilt angle from those readings. There's a latent temperature reading. Light level, the LEDs on the front are able to detect light as well as transmit it. And there's a microphone for measuring sound, and there's a magnetometer for measuring magnetic field. Let's see how this works. I'm going to load up a setup. Okay, now I'm going to this is the iLOG software, and we can do most of what we need to do, especially if we're beginners, by using the welcome menu. When we've got a bit more experience, we can just use the normal menu at the top. Right, this is waiting for my microbits to be connected. So if I plug this in here, okay, and press reset on the microbit. No joy yet, so let's come in here. This makes sure that the connection is going to be fine, and that's the case now. I'm going to collect data in so-called real time. In other words, we want to see the data on the screen simultaneously with it being collected. And here we have symbols for the accelerometer, for the tilt angle, for the temperature, for the light, and the sound level. And I'm going to log it for a period of 60 seconds. So that's all ready to go. I'm just going to adjust the axis a little bit so that we can see things nicely. This control panel here has got a very obvious starting button. So off we go. And the data is coming in, it's being plotted on the screen at the same time. I can join all the points. It's a bit of a mess, so it'll be better if we look at just one set of data at a time. This is the accelerometer. It measures movement. Here is the tilting angle. So as I rotate it, okay, we can get readings of the angle of tilt. Here's the temperature, not changing very much, currently running at about 26. The light level, if I point it up towards the light here, yes, it's measuring light there. And sound, well, that's all the rubbish that I've been talking for the last few minutes. Now, when we get to the end there, now comes the useful business of actually looking at the data and trying to find out interesting things about it. We can join all the points up. It's a succession of data logging is a succession of readings at regular time intervals. But if we join all the points up, then we can see something, a pattern in what's going on. I'm going to choose the roll example here. Now, I can alter the axes to suit what I want. I can squeeze them and stretch them according to what my focus, what the focus is that I want to make. I can alter the scale in a variety of ways. The most convenient one is to zoom in. Getting information now. If I click on this button here, I can read off the readings. Of course, all the readings are stored on this dreadful table here. But what a mess it is! I can simplify it a little bit, but let's have that back. As we move the cursor across the graph, we get readings showing up. Down here, I can ask it to show the name. And what are the units? There are the units. This is 20 degrees of rotation. The bars on the right-hand side here, these bars here are an attempt to help children make the connection between a value that's being, a reading that's being sent from the data logger to the graph. Those of us who are used to graphs can make that translation very in a very straightforward way, because it's very familiar to us. But the whole idea that we've got a succession of readings that go up, they go down, and they're ordered in time along the time axis, these bars here are an attempt to assist that process. Now, what else can I find from the information here? This menu up here, the Analyse menu, has got a variety of tools for getting even more information. So what is the time interval between this low point and high point? 5.1 seconds. What's the time interval between those two high points? And so on. So we can measure time intervals off very, very conveniently. We can see that there's the pattern of change. We've got increases and decreases at various speeds. I've got a tool here for measuring the rate of change. So here we are, -33. So it's reducing at a rate of 41 degrees per second. A double click establishes the first point. If I go, what's the average rate of change right up to there? 18 degrees increasing per second, and so on. Of course, it's very common for us to associate the slope of a line with rate of change, and that's what this tool helps us to do. It's showing us the gradient at different points. It's a rather jerky one, this one, but it is also possible to smooth the line. I can look at that later if there's time. A variety of tools here. I've got a list of them here. Here we are. If I'll just show you one more. It doesn't have very much meaning in this context, but the area underneath the graph sometimes has a useful physical meaning. I'm thinking of voltage and current experiments where the area indicates the charge or the energy. Okay, so those are some of the analyzing tools. There are also some curve fitting tools, curve smoothing tools, and a calculator for getting more data. Now, if we can use external sensors, the whole variety of experiments expands that we can do. This is a DIY job of mine where I'm just using a thermistor and a resistor in series, and it's a simple potential divider circuit. And because the microbit is equipped with these very convenient 4mm sockets, it's very easy to connect your own sensors up there, and I can use that as a temperature measuring device. However, if you want to measure temperature, for example, in hot liquids, I don't know how my cough is doing these days, but at this moment, here's a nice temperature sensor, a temperature probe from the Micromaker people. And we can plug this into the Micromaker board. It goes into that edge connector, and here goes the temperature sensor can go in there. And if I now go back to my welcome menu, and I'm going to change the board, I'm not using the Microbit on its own, I'm using the mini innovation board from Micromaker. Okay, here we go. And I'm going to collect some data. What have we got here? I want to measure temperature. Okay, so we're going to measure distance and light in a moment, but let's start off with temperature. So logging, here we go. We're all ready for that. So I'll just switch off distance and light, and let's see what my coffee's doing at the moment. It's gone pretty cold. It started off at 60 degrees, but it's gone pretty cold. Anyway, there's a temperature probe which can be used in a whole variety of experiments in a science context. Here's another very useful sensor. It's the ultrasonic distance sensor. Sends out ultrasonic pulses, and it can measure the distance of the nearest reflective object. I've got that clipped on the board there, and there's a light sensor here as well. I'm going to plug that in so that we can begin to take some measurements of distance. And let's stop that. Distance, and where are we? No, don't need all that. I'm going to measure distance and the light level. Okay, let's start off. Off we go. And so this is an object getting closer. The red trace at the bottom of the graph there is the distance, and the blue trace is light. Right, switch on my torch. The light clearly increases quite dramatically. So those are some measurements that are possible with an external with external sensors. The scale is not very satisfactory. I can easily improve that using the tools that I showed you just now, and so on. Now, there are a variety of add-on boards that you can use for using external sensors. The Envirobit is one that I found very useful. Here it is. It's very useful for environmental measurements, very topical at the moment. We've got a device here, a sensor that will measure pressure, atmospheric pressure, humidity and temperature. There's a light sensor and a sound sensor as well. And I used this overnight to monitor what was going on the windowsill of my bedroom. And here's the answer. What we have here is sound. It's a pretty quiet neighborhood. Humidity and the light. Well, I started it at 8 o'clock last evening. So it was getting dark. Well, it was already dark at 8 o'clock, of course, but the temperature clearly is declining. And the lowest temperature was, there we go, the lowest temperature was 2.3. In the morning, what time did it start registering light? It's 10 hours after 8 o'clock. So that looks a bit like 6 o'clock to me when at first light. Okay, so environmental measurements, very, very convenient. Now, clearly, I didn't have the computer hooked up to the Microbit all the time, and that's a very important. It's a very important facility to be able to be able to set the microbit up to record the measurements completely independently. And I'm going to take us back to using the microbit on its own. Okay, and I'm just going to use, in this case, I'm just going to use the accelerometer. Because what I'm proposing to do is to investigate a simple pendulum. And what I've got here, my microbit is going to be the pendulum. On the back here, I have blue tacked some batteries. Here's the battery connector. So it's now completely independent. And I can send instructions to it from iLOG. Okay. So I've chosen the sensor that I'm going to use. Remote logging. Remote meaning that the microbit can work remotely from the computer, all on its own. Now, this is a different microbit, so I must just allow the system to connect with it. Okay. How long am I going to swing it for? I'm just going to choose a short 5 seconds. And if I click that ready button, the instructions now have been sent to the microbit. And to start logging acceleration readings, I just have to press button A, 3, 2, 1, and for 5 seconds, it's going to log the data. All done. Now, let's do the real experiment. I'm going to swing it first of all with a fairly long piece of string. Right, I'm going to press button A. So we've started. 3, 2, 1, off we go. And after 5 seconds, we should have some data. Now I'm going to repeat it with a shorter pendulum string. So here we go. Press button A, 3, 2, 1. And we're all done. Now it's time to have a look at the data. We reconnect back to the welcome menu, and I'm going to collect the data from the logger. It's connected here. And we've got a series of files. The most recent one is always at the top. So if I download, there we have it. That's the data for the most recent one. That was for the short string, wasn't it? So if I look at the time interval between, say, 1, 2, 3, 4, 5, 6, 7, 8, 9, that's 10. So that was a period of 4.3 seconds. So 0.43 seconds, or 430 milliseconds if you prefer. That was the short pendulum. What about the longer one that I did initially? Download from the logger. Off we go. That was the previous one. Oh, right. Let's have a look at one. That I did earlier. Here we go. Yes, and this time the time interval is so Okay. Right. So this is remote logging, and I'm looking at the time. I'm coming up to half an hour, so I think it's time to start letting people. I think I'll save the oscilloscope. There's a lovely microphone on the Envirobit, which allows you to observe both sound levels and sound waves, and iLOG has a facility for looking at the frequency spectrum as well. So if I can change now the I can change the camera so that you can see me, and if people would like to unmute their their microphones, then perhaps we can have a conversation. I would like to show you some of the activities that have been built into iLOG. How are we doing? All right, John?
Brilliant, yeah.
Yeah.
Well done, Laurence. Keep it up.
Okay. So what we have here is a whole range of activities. These comprise some of the questions that you can ask pupils that we want to investigate using a data logger. How long do batteries last? What about this one? I did this some while ago with an old-fashioned torch bulb. We pop a torch bulb into a shoebox, a light sensor. You can use the Envirobit light sensor, the built-in one if you wish, and the battery is connected to the bulb, and you just leave it on. How long do we leave it on here? For 15 hours or so, and we can see the difference in performance. I've merged these two sets of data so we can see the difference in performance of the two major types of cell that we can buy. Any questions on that? Here's another one. How steady does a clock tick? Well, no surprises. In this particular case, I put an old-fashioned clock inside. No, it's not an old-fashioned one. No. This is a digital one inside a box, and just listened to it. Just recorded the sound from it, and here are the ticks. How one, yes, that's 1 second, and so on. Here's an old stage in science lessons. Animals huddle together. Why do they do this? Well, we've seen the penguins do it, but a whole variety of animals do this, and we can simulate what they're doing by clustering some test tubes and pouring hot water in them and seeing how they cool down. And what we have here are some instructions to help pupils set it up. Here's the temperature of the lone tube on its own, and the other probes are there so that we can directly experience the changes of temperature. Right in the middle of the huddle, that clearly is the tube that retains its heat longest. At this stage,
that experiment many times.
Yes, I'm quite happy, to answer questions at this stage. This is one. What materials are going to be best for muffling a sound and insulating sound? Very simple one there. Once again, with a sound sensor. Counting people coming into a room, we can use a light beam. If you walk through a light beam, clearly it's going to change the light being detected. And here's a simple example of how that can be investigated. And here's another example showing how the instructions are provided for the children to set up an experiment. I've got a hot cup and a cold cup. I put the probe in one. There's the cold water. Put the probe in the hot water and mix the waters up, and we get somewhere in between. And these heat experiments, insulation, these heat experiments are very easily serviced with data logging, where you want a whole series of readings over a period of time. So there are more, but let me come back to my PowerPoint. There are over 40 sets of sample data with iLOG, which allows you to practice looking at the data and doing useful things with it before you've actually collected your own data. Finally, if you like these graphs so much, you can import data files in CSV format from any source. I think the version 2 microbit has a facility for downloading CSV files. And if you want some really nice graphical representation of the data with all the tools for examining it and so on, you can import CSV files. It's a very tolerant importing regime. The other day, I put my bank account CSV file in it, and it's very interesting to watch the graphs showing my balance going down each month. But that's also possible. So there we have it. That's my pitch here. If I'm asked to say, look, what do I think is so important about data logging? Its ability to record data for fast events or over very long periods. This really extends the opportunities that we have for observing physical phenomena and making measurements. The visualization on the graphs is very important to me, because once I've got the data, what does it mean? I have tools in iLOG to help me make those observations and draw conclusions. But for pupils, of course, it's a wonderful tool for encouraging curiosity and prompting questions and enabling you to find answers. But as with so many educational tools, the teacher is so important. The input of the teacher is so important for creating the culture and the habits in the children, so that the tool can do the job that we want to. How about that? Have we got some questions logged on the chat?
I haven't been. Can I just first of all just thank you for that? That was brilliant. Really. Can I just ask first of all, did you develop the software, Laurence? You said you added some functionality.
Yes. The first version of Insight data logging software was published by Logotron in 1992.
Yeah.
And I've been successively upgrading it. Logotron went out of business about 10 years ago, and so I took on the mantle myself to carry on developing it. And as you mentioned earlier, interest in data logging has waned somewhat in recent years, but it's wonderful when the microbit came along, because it gives us an opportunity at very low cost indeed, to revitalize all of those ideas that we were pioneering, dare I say it, 30 years ago.
I had an Ofsted inspector. I got really good feedback for lesson. This was about 1996, and I'd made these ramps, and I was using data harvest, and we're measuring acceleration, putting And it was just really impressed that they were doing this data logging. And
Yes.
but when I talk to people, I talk to a lot of schools, and there's a lot of this kids sitting in cupboards. So it's such a tragedy, and it's because the teachers don't know how to use it. But I think with the microbit, you know, because it's being used a lot in computer science now, the problem we've got is science teachers don't have that support that we're getting with computing now. And I guess you've got two different audiences now sitting both of them. And you've got your natural scientists and you've got your computer scientists. And the computer scientists might be sitting there thinking, well, I won't be doing huddling. I might be doing a weather station. So I can maybe use that that add-on, you know, for the environmental, which looks really good actually. I think, I mean, I like the fact that you could do it. I think it's something like about 20 kilobytes of storage. There's a little bit of storage. There's not a lot, but when you store in text, but you could, I guess you just Bluetooth the data when it's.
No, we don't use Bluetooth. It's but Bluetooth slows everything down, unfortunately. So if you want decent real-time data logging, you've got to use the USB.
Right.
But in terms of the data storage, we have optimized the number of items of data that you would typically collect in a data set. It varies between 500 and 1,000 items, but that could be for up to 8 channels. And we can cope with all of that. There seemed to be no point in collecting more than 1,000 items when you've only got a resolution on a screen of 1,000 pixels or so horizontally. So we manage all of that so that you choose the duration of your experiment, and the sample rate is adjusted so that the overall commitment for memory storage is roughly the same.
And I suppose from the computer scientist point of view, we talk to students about input and output devices and what the CPU is. So obviously all of your sensors are all input devices in the physical world. So in terms of me thinking now, if I was doing a lesson, you know, instead of just having a PowerPoint, we could talk about, and this is the sort of thing that we're doing at the moment, we're doing about the accelerometer, you know, and that fact, and there's all sorts of web-based things for it. But you can obviously take it a little bit more with the sort of work that you are offering, aren't they? They can log, you know, temperature changing over time, which is it's all still input devices, so it's all really useful.
The temperature reading that you get from the internal microbit,
isn't it?
It is not very satisfactory in my opinion. It's okay for ambient temperature, but it's always a couple of degrees more than real room temperature. It's the average temperature of the board. So
it's a CPU, isn't it? It's the one built into the CPU that it uses, isn't it? So it's always a bit warmer.
Okay, I'm proposing to put the PowerPoint up on the CAS resources repository fairly shortly. This session has been recorded. I'm not sure how we make that available, but it can be available clearly.
I can email it out to everyone now. Can people, because there's a thing with CAS, you don't get people's emails afterwards. So if I put j.lam at stem.org.uk, if you email me, I can just share it with you. Afterwards. Are there any lesson plans, you know, for computer science? I guess there's quite a lot around for science, but for computer science to be able to use these, to use the software, any?
Yes, I come from it like yourself. I was once a physics teacher, and I come at it from a science point of view. So. Having looked at the schemes of work that are published for the National Curriculum in Computer Studies, there are many possibilities there, but I haven't addressed those directly with the materials that come with iLOG. All of the instructions for the experiments and ideas for things to do with the data. It's all built into the program, into the screens. If people want to email me, this info at Insight Resources will catch me, and my website for iLOG is there. I'm happy to answer any questions via email. I'm happy to do more Zoom sessions if people would find them useful.
I think it's definitely something that there's both the science and there's the computer science. So one of the areas that I know for me, because I work for STEM learning, so we work across the Science Learning Partnership as well as the Computing Hub. So we are trying to get everybody working together. So going forward, it might be something that I can, bring you in to work with a group of scientists, perhaps.
Right. Mike's got something to say. I think Mike's got something to say.
Yeah, I just wanted to say that don't forget to say that there is a trial version that people can take away and have a look for a month or so.
Yes, I've sent the URL for that to John as well. So
yeah, I don't have people's emails. That's a problem.
Oh gosh, right.
You'll have to give me. Can you? If you just email me and I'll share that with you.
Yes.
I've emailed. You can. It's the CAS thing. You can email people before the event. But once the event's happened, I'll try immediately afterwards. It might be okay.
Okay.
Yeah. In fact, I'll try and do it now if you take some questions, because strictly speaking, it hasn't finished. So I'll just take a minute to do that.